Okay, this is lesson 3.2, least upper bound, greatest lower bound. And we're going to go over Theorem 3.4. And basically that states that if S basically is not an empty set. So in other words, set S, here's set S, and it's got some numbers in it. Okay. And set S is a subset of the all real number set. Okay. Has a upper bound, we'll give that uppercase M. So this is our upper bound here, M. And then, so the theory is stating that then it has a least upper bound, then it has a least upper bound. U. So that means that it has, we're going to say that this least upper bound, the absolute lowest upper bound. So this is like the bottom of the upper boundary. And U. That is, there is a unique number. There is a unique number U that is an upper bound for us, S. That is an upper bound for set S. That is an upper bound for set S such that no number such as U prime is lower than U is an upper bound. Is an upper bound for set S. Okay, so what does that mean? That there's going to be, so we're saying here that U is the least upper bound. So there's other upper bound numbers here, but U is the least upper bound. Well, what on earth does that mean? Well, think of like upper bound for an economy. Like upper bound is A's, right? So the least upper bound would be a 90. So there is nothing lower, so 90 would be the U. So there is nothing lower than 90 that would be still an A. All right. So this is saying that U prime, so there's other numbers lower than 90, right? But they're not an A. So this is saying U prime is less than U, but there is no number U prime less than U that is still upper bound. So there's no number less than 90 that's still an A. Okay. Okay. So 90 would be our least upper bound for A's. So our proof. So then, therefore, our proof would be, I'll just take this off. Therefore, our proof is we're going to use the nested intervals theorem. Use the nested intervals theorem that if m, which is our uppermost, our boundary, right? M is an element in set S, then U equals to M, since there for all elements in set, all x's that are an element in set S, is x is less than or equal to U, and if U prime is less than U, then U prime is not an upper bound. Is not an upper bound. Is not an upper bound since U is an element of set S and U is greater than U prime. So our least upper bound is greater than anything lower than that. Okay, so basically the nested interval theorem gets into where we have where basically we cut it in half, and then we look at intervals and cut it in half again and look at intervals some more. And so from there, we can prove the theory least upper bound and greatest lower bound. So basically, and then in that case, then there's also another number where we have an L, we'll call this L, is the greatest lower bound. So greatest lower bound, you could say, is an F. So the greatest lower bound would be 59.9 would be the greatest lower bound. So it's still an F, 59.9 is still an F, but anything above that, like a 60, now 60 would be a D, right? So that would not be an F. So 59.9 would be the least upper bound, and anything below that is still an F until you get to M, which would be 0, where an M would, lowercase m is 0, uppercase M would be 100, let's say. Okay, and so that's pretty much all we're going to do as far as theorem 3.4 is concerned, and now we're going to get into some example